All right. We're going to talk about methods of proof. Part 2. Proof by induction. We used to teach a little bit of induction in advanced pre-calc, but we don't anymore, which is kind of unfortunate. I remember learning proof by induction when I was in my pre-calc class, and it's kind of fun. All right, so proof by induction is often used when we want to show that something is true, some property holds true for all integers. And the basic idea of proof by induction is we show that our, and maybe I'll write down up here, so we usually to show something about all integers. And as another example, the Fibonacci sequence, it's a sequence of integers. You often use proof by induction to prove various properties of the Fibonacci sequence, the numbers in the Fibonacci sequence. So the idea is that we show that the proposition is true when n equals 1. So for our first integer. We call that the base case. So we show that it's true for n equals 1. So you basically, with that, often with that, you just plug in a number and say, see, this works for this number. And then you assume it's true for some other n. So you show it's true for the first case, and then you assume it's true for some other case. And then you show that this implies that it's true for n equals k plus 1. Once we do this, we know since it's true for n equals 1, for n equals 1, well, if it's true for one number, then that implies it's true for the next one. That must mean it's true for n equals 2. Well, that implies, since it's true for the next number, n equals 3, et cetera, et cetera, et cetera. So that shows that it's true for all integers. So the kind of the visual for proof by induction is you set up your first domino, and you show that if you tip that domino, all the rest of them have to tip. That's kind of the idea. If it's true for one, then all the rest are going to tip. Proof by induction comes up frequently when you're working with sequences in series. You want to show that some term of a sequence or a series has some specific property. Well, sequences in series, we index those with integers. So often you use proof by induction when we're dealing with sequences in series. All right, so let's look at an example of how we would use proof by induction. So my proposition here is that n squared plus 5n plus 6 is even for all n greater than 0. And n is an integer. So we want to show that when we square an integer, multiply it by 5, and add those together and then add 6, that always turns out even. All right, so our first step, our base case. Show that's true for n equals 1. For n equals 1, we get 1 squared plus 5 times 1 plus 6 equals 12. And we know 12 is even. So it's true for the base case. And then for our what we call our induction step, we say assume that k squared plus 5k plus 6 is even for some k greater than n, greater than 1. Assume that is true for some integer greater than 1. Now we're going to show that this implies that it's true for k plus 1. So what we're claiming here, I'm going to say this means that k squared plus 5k plus 6, this is even. So that's going to be 2 times some other integer. So that's what we mean when we say that this quantity is even, that we can write it as 2 times some integer. Now, our third step is we have to show that this implies that k plus 1 squared plus 5 times k plus 1 plus 6 is even. So if this is true, we want to show then that it's also true for the next one, the next integer beyond k. All right, so what we're going to do is perform this operation, and then we're going to be able to kind of gather some things together and make a substitution. All right. So I'm going to say we have, when we do this out, I'm going to say k squared plus 2k plus 1. That's what I get for the first term. Plus 5k, 5 times, so 5k plus 5 plus 6 when we multiply this out. What I'm going to do is gather the terms so that I have this again, because we've assumed that's even. So I'm going to rearrange this, and I'm going to say this equals k squared plus 5k here plus 6. And then what I have left over is plus 2k plus 6. And I'm keeping this together because we said before that we're assuming that this is even. So we have this 2m by our assumption. So we have this equals 2m plus 2k plus 6. And I can write this as 2 times m plus k plus 3. M and k and 3 are integers. So we have 2 times an integer. So that tells us that this quantity is even. So I'm going to say which is even. So k plus 1 squared plus 5 times k plus 1 plus 6 is even if k squared plus 5k plus 6 is even. This shows that the statement must be true for all n. So we know it's true for n equals 1. If it's true for n equals 1, then it has to be true for n equals 1 plus 1. Then it has to be true for 2 plus 1, 3 plus 1, et cetera, et cetera, et cetera. So we've shown that it's true for every integer. Isn't that slick? Proof by induction is really nice. Yes?
So why do we use the variable for k for this? Because that just seems like it convoluted what you did. Because if all you're doing is proving that it works for n plus 1. So if it works for n, and we set n equals 1, we can demonstrate it's true for n equals 1. And then all we have to do is demonstrate it's true for n plus 1. Because that means any n will be okay.
If you show that it's true for n plus 1, what you're doing, basically what you would be doing is showing, okay, it's true for 1. Now I'm going to show it's true for 2. Now, so you want to show that it's true for just some, you assume that it's true for some k that's bigger than n.
Okay.
So you want to be as general as possible. Yeah.
You said there will be a proof on the test, right?
Mm-hmm.
Are you going to tell us which type of proof?
Even and odd. It has to do with even and odd.
Oh, okay.
So, and the nice thing is you can use multiple different techniques to show it. All right, let's look at another one. Sometimes now with proof by induction, where they get a little tricky is sometimes you have to do a little kind of manipulation in this step, like a +1, -1 kind of thing that we've done in our integrals to get things to work out the way you want them to. But you can do that algebra, that little arithmetic trick, to get the things to work out the way you want to. All right, so let's look at another example. So I'm going to say my proposition is that 1 plus 2 plus 3 plus ... plus up to some n equals n times n plus 1 over 2. Does this look familiar? It's not multiplication, it's addition. This is an arithmetic series. And in pre-calc, I showed a different proof that the sum of n terms is n times n plus 1 over 2, an algebraic proof. Now we're going to do a proof by induction. So our first step, show it's true for n equals 1. Well, what we're saying is, does 1 equal 1 times 1 plus 1 over 2? Yes. So we're good there. For our second step, we're going to assume that 1 plus 2 plus 3 plus ... up to some k equals k times k plus 1 over 2 for some k greater than 1. Now, what we want to show that this implies that 1 plus 2 plus 3 plus ... plus k plus 1 equals k plus 1 times k plus 1 plus 1, k plus 2 over 2. That's where we want to show that this implies, when this is true, that that implies that this is true. All right, so I'm going to take our previous assumption and just add the next term. So I'm going to say k times k plus 1 over 2 plus k plus 1. We're just adding one term here, and we're going to work with that. Well, that equals, when I multiply this out, we need a common denominator here, so I get k times k plus 1 plus 2 times k plus 1 over 2. And that equals, we're going to multiply this out, k squared. I get a k and a 2k here, plus 3k, plus 2. So I get the 2 here, all over 2. And do we see what happens here? This is k plus 1 times k plus 2 over 2. So this is true. Then the next term, the sum of the next, adding k plus 1 to this thing, gives me k plus 1 times k plus 2 over 2. Yeah?
I'm confused about where you put down plus k plus 1.
So what I did was I said, well, we know that from here, whoops, 1 plus 2 plus 3 plus dot 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 up to k, whoops, equals k times k plus 1 over 2. So we're assuming that's true. So I want the next term, I just want to add one more integer. So I'm just adding k plus 1 to that. So I'm going to say, on the other side, I'll put one more thing here. So 1 plus 2 plus 3 plus dot 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 plus k plus 1 equals that. So we're just adding this to each thing that we said was true in the first place. And then we just rearrange the right-hand side to show that that is k plus 1 times k plus 2 over 2. So, and I'll put this down here, 1 plus 2 plus 3 plus dot 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 plus k plus 1 equals that. And that's what we were trying to show. So that this altogether, this shows that this is true for all n greater than 0. So another way to show that the sum of an arithmetic sequence is the formula that we talked about in pre-calc. All right, questions on proof by induction. So just two induction proofs for homework. We want to show, for both of these, show, and I'm going to say by induction. One plus 3 plus 5 plus dot 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 plus 2n minus 1 equals n squared for n greater than or equal to 1. So the sum of odd integers is n squared. And 2, sum k equals 1 to n of k squared equals n plus 1 2n plus 1 over 6. So these follow along pretty much exactly like the examples we did. So we have these nice summation formulas. All right, there we go.